Okay, cool. We can get started. So my name's Matthew. I work at the University of Queensland and have been involved in WildObs from the very beginning. And we've had three different webinars now explaining what our platform and services and products are doing, what problems they're solving, how to use them, how they're compatible with other systems that you might already be using. And so this is the third session where we're going to focus in on choosing the right AI model for your wildlife monitoring needs. And what we're going to do today is I'll give a quick introduction about how this fits into the workflow more generally. And then we're going to hand it over to our computer scientist who has a PhD in computer vision to actually talk about how these computer vision AI models work. Then we'll have a case study about people using these models, and that will be done by our collaborators from Bush Heritage. And then we'll have a few more case studies and end it with questions. So that's the overview. Okay, we go slide. I'd like to start by acknowledging the traditional owners of the lands on which we meet, travel, and conduct our research, and acknowledging their continuing connection to culture and pay our respects to their elders, past, present, and emerging. So all this work is done with a huge team, and what's really been productive and fun is that these people come from a wide range of backgrounds and organizations, and coming together to build a real fit for purpose, user-focused um, set of services and products to help people camera trap, share data, and make biodiversity monitoring more productive. So I just want to shout out to the whole team here. So quick housekeeping as well is if you wouldn't mind during the recorded webinar, which is the first 25 minutes, to stay muted, and you can add your questions to the Q&A, which is one of the options next to the chat, and we'll go through those at the end. So what is WildObs? So we offer an ecosystem of products, tools, and services all completely Australia focused with all data sovereignty being done here on our, so everything is stored on our soil on the national government platform. That research platform is called the Nectar Research Cloud, and we use cloud compute. And so we're really trying to take people through the entire life cycle of camera trapping all the way to the government end users who are doing the state of the environment report or to the very end user who's in a national park and wants to make a decision about how management should occur, or to the end user who's an academic who wants to publish a paper on a particular research topic in ecology or conservation. So to break that down to different steps, you start your camera trapping journey with deploying your cameras. And so we're working on a metadata collection phone app. We're doing that with DQ and Turn. And then you're going to have your images and you're going to want to process them. And so we first offer one single platform. It's called our image management platform. And this includes starting with cloud storage. So you'll upload your images. Then you'll get to choose which computer vision models you'll run. And that will all run on the compute with massive GPUs provided by us. So that means you don't have to have a really powerful computer. Then you'll want to verify the identifications, at least for the species that you are interested in or that you think might not be performing well. Then you're going to download your spreadsheets and you're going to do that in the CamTrap DP standard, which means you're already set up to share data because it's an international standard. So we have a database where you can contribute data. So if you have legacy data, we provide a portal with a questionnaire that allows you to convert your data into the standard really easily. And then it allows you to identify where camera trapping has been done. So you can request private data, or you can download directly public data, and you can do that through our WildObs R package. Now, when you have your data in this CamTrap DP standard, you can load a dashboard of all your personal results automatically. So that allows you to do your own analyses and visualizations and is very easy to share, both for your government reporting requirements or your grant reporting requirements, or maybe just for collaboration. And some of the other tools that we have are a tagged image repository. And this is where computer scientists can go to train new models. That's where they find their images. And a computer vision library where we have a set of models that you can run offline. You don't have to use our image management platform to run or to train a model or to run these models if you don't want to. Yeah, so really taking people through this entire life cycle. So on this talk, we're really going to focus only on the image management platform and actually only one aspect of that, which is which computer vision model to choose. And so the image management platform has a variety of steps. It goes from uploading your data from your SD card to the cloud, and we offer that in a bulk upload scenario. So unlike Wildlife Insights or some of the other platforms you might have used, what you'll do with us is you'll just link it to a folder on your computer, and it will sync even while your computer is turned off or shut down once you've set that up. So then in every single computer vision pipeline, the first thing we do and every system does is run it through Megadetector. And that's just going to tell us if you have an animal. If you have an animal, then it goes from a detector to a classifier where we cut out the snip, that's the little cropped area of the animal, and we pass that to the classifier and it gives it its ranking, its accuracy. That goes then to humans to validate. The data is then annotated where the tags are all added to that. Maybe you want to also add tags like the number of individuals, and then you can download that and store it in the WildObs database or download it to your local drive, whatever you want. And we're going to go into a lot more detail here. And with that detail, really thinking just about that computer vision step, I'm going to hand it over to Dr. Renuka Sharma. She's a computer scientist with a PhD in computer vision from Monash, and she's leading our efforts here at WildObs. So go ahead, Renuka. Thank you.
Thank you, Matthew. Thanks for the introduction. I'll start with why we are using computer vision or AI in our image management platform. So there's a big scalability challenge when it comes to ecologists and camera trapping community. So different conservation efforts, they collect millions of images over the entire year, and they have massive data to analyze, and it is really difficult to do it manually. And most of the times, this data has lots of noisy data points, like sometimes the vegetation moves and the camera just captures a lot of pictures. And also it captures pictures for species which are not of concern for the camera trappers from that organization itself. So lots of filtering is needed, and doing it with the help of human efforts, it takes lots of time. With the help of AI or computer vision, we are trying to reduce this effort from months to days, and we are trying to get the efficient outcomes without compromise. Like Matthew mentioned, we are using computer vision in the imaging platform, where the first step when you upload your deployments, which is a collection of camera trap images, the first step that it goes through is the detector, which we have different versions of mega detector and different detectors like YOLO as well. When it comes to mega detector, it detects where wildlife, human, blank, or vehicle is present in that image. And if there's a wildlife or animal present in that image, we take we crop out that part of the image, and then we track those crops across the sequences, across the images which are consecutive, and create a sequence out of it. And on top of that, we apply a classifier which provides a label to these crops. Here is the difference between the detector and classifier. Detector is used to find if something is there, like it's drawing the bounding boxes around this cassowary. And then when the snip is transferred onto the classifier, it will be able to provide the label to that bounding box and also give its confidence score, how confident it is in this particular prediction. We have different global and local classifiers since we are building our platform focused for Australian purposes. We have national models and local or regional models. National models cover broadly all the species which are in Australia. That is our aim. And WildObs National is one of the models, and we are hosting AWC 135, which is the model from AWC organization. These cover all these species broadly, but they may lack precision for for species from specific habitat or regions. That's why we have local or regional models. They are balanced for specific geographies and specially trained for just the species which are in that small habitat. And if you're sure about what habitat you or geography you're uploading your data from, then you can choose those models particularly. Here's an example of two different such classifiers. So this is an image of giant white-tailed rat, and our national model predicted it as black rat, but the regional model predicted it correctly. So this is because of the dataset imbalance and also which happens when we create such big, large models in comparison to smaller models. WildObs image platform provides access to many computer vision models. So including AWC 135, we have only the detector model as well, and different variations of local and global models. So you can select this model at the project level stage or also at the observation level. The common approach that ecologists follow is they pick a default model and then run it on the full data set and safely assume that it works. But sometimes it leads to poor results because not all the models are designed for every use case. That's why today I want you to understand how to find the right model for your purposes. So our platform is going live on June 1st, and at that time you will be able to have this website open to you. You will go on image management platform, get started. That's where all our WildObs hosted CV models are placed. For now, they're also on Hugging Face WildObs organization if you want to have a look and run on your local computer, and also to know more about what species are covered in every model that we have built. So the first step that you have to do is create a test data set. That test data set should have a collection of all the species that you want to analyze from your data set, from your camera trapping experience, the ones that are present in that particular region. Try to get 200 to 1,000 images each for every species. After that, onto our platform, create separate projects for every classification model that you think might work for your case. So let's say in this case, we are choosing SpeciesNet, WildObs, AWC 135. If you're choosing 3 models, you need 3 projects. And select that project, select that classifier at the project level. After that, you create the deployments. By deployment, we mean the camera information, which is optional. You need to provide the location and the image files associated with that camera trapping experiment. And after it has been uploaded, you will see the status bar progressing, and our computer vision model will be applied on it in the background. You don't have to keep your machine open all the time. Once you can see that your files have been uploaded, you can be rest assured that the processing will happen on our cloud compute, and you don't have to worry about anything else. So after a while, you will be able to see this green annotate button. You will be able to click on it and actually see how the annotations have been done. The next step, after you are satisfied with the results, is to export the data. You will create an export and you will be able to download a zip file. So this zip file will be in camera trap TP format, which is a collection of these 4 files. And the file of concern here is the observations.csv. This will contain the information about all the annotations that has been done by our computer vision classifier. So if you look into that CSV file, these are the columns, and you will be able to see which model has classified it and also what is the probability it has provided. We have media.csv file, which will contain the file path for the media files that you have provided, their capture method, all the information that you have been able to provide at the project level. Now coming to analysis step, we have created this Git repo where there's a collection of, we have a Python notebook and also a Python manifest file. So you can follow these 4 commands or the Python notebook to be able to create this particular evaluation report. This is an HTML file you will generate for every model that you have selected for exploration. So, and this is to assess how your model has performed, has there been any misclassifications, and it's a thorough report. Here, we are trying to focus on all the metrics that are of concern while evaluating model performances. You have recall, precision, and F1 score. Recall starts from the ground truths that you have. Let's say you have 5 cat image, you start from there and see how many of those your model is able to identify. And it highly penalizes false negatives. Precision assesses the credibility of the model, how accurate the model, the classifier has performed on the basis of the test data that you have provided it, and it penalizes false positives. F1 score, it is a balance between recall and precision, and it penalizes both false negatives and false positives. And if you are unsure which metric to go for, F1 score is the best one, and also it works best for imbalanced dataset in case you're not able to achieve 200 images each or 1,000 images each for every species. Now, for case study, I would like to introduce Colin, who's a conservation systems developer with Bush Heritage Australia, one of the WildObs project partners. Part of Colin's role at Bush Heritage is facilitating the effective adoption of AI-assisted camera trap monitoring. So over to you, Colin.
Everyone, and thank you, Renika, for the introduction. Bush Heritage owns and manages conservation reserves in a wide range of ecosystems around Australia, and we do a lot of camera trapping, and for many reasons, but typically for adaptive management purposes with a focus on invasive species. And we're increasingly making use of AI to try and speed up our image review process. One of the key goals around this is trying to reduce that time gap between when we capture the data and when we get that analysis result. And this really speeds up and enables our adaptive management cycle. In our experience using AI, we've found that the models sometimes generate unexpected errors that a human observer wouldn't normally make. For example, misclassifying an emu as a crocodile or something really unusual like that. And outliers such as this can create a sense of mistrust in the models and AI more generally. And this makes us a bit tentative about using it for our real-world monitoring programs. On the other hand, there's sometimes a tendency to invest too much trust in the models, and this can be quite risky and lead to poor results. So what we're aiming to do is shift away from that anecdotal assessment of model performance and more towards a data-driven or scientific assessment. And we're following a general principle that all models are wrong, but some are useful. Bon Bon Reserve is one of our large conservation reserves in the arid rangelands in South Australia. The camera monitoring program at Bon Bon is mainly designed around invasive species like cats, foxes, and rabbits. So one of our first goals was just to identify which model was best suited to this particular location and the species of interest for that monitoring program. Our second goal was to design a targeted validation workflow to compensate for the model errors. And there are a few advantages of WildObs which make it easier for us to run this type of analysis. Firstly, the ability of the platform to host multiple models, including those that have been developed by the WildObs team, but also user or community contributed models from other providers. But also the standardization of the data format in CamTrap DP format and the standardization of the taxonomic species names. So we first collated a test data set. We used 1,000 images each of each species, and we uploaded these to WildObs and processed them through 3 models. These were the WildObs national model, SpeciesNet version 4, which is a global model, and the AWC 135 model. We exported the data in CamTrapDP format and processed this through the model evaluation tool to generate detailed reports. And we studied their reports and assessed these results in detail and reviewed the pattern of errors in each of these models. So our test data set was fairly simple. We included the target species, so cats, foxes, and rabbits. We also included species which were not relevant to the monitoring program, but were commonly occurring at that location, in fact, making up a large portion of the images captured on the cameras. And we also included blank images just to create more noise in the data set and to simulate a real world example. So firstly, looking at the recall. So recall really tells us how many true detections of each species were correctly identified by the model. For us, this is really important because we don't want to miss genuine detections of those species, and this would underestimate the scale of the threat. So in this case, for recall, AWC 135 performed very well for cats and foxes. However, the way the model is structured, it was aggregating the rabbits into a broader taxonomic group, so we couldn't get a detailed result for recall. SpeciesNet was also aggregating some of the rabbits into a broader group, but identifying some of them correctly. So we got a low value for SpeciesNet as well. Looking at precision, so this is more around the rate of false positives. So for us, we care about precision because we want to avoid spending a huge amount of time sorting through the noise and finding those true detections. And in this case, SpeciesNet achieved perfect precision for all of the species, meaning that when it made a prediction of that species, it was correct. However, given that recall was very low, it meant that a lot of the genuine detections were missed. So the best way to approach this was to look at the F1 scores, and this provides a balance between recall and precision and gives us an overall measure of the model performance for each of those species. And AWC 135 was clearly the strongest performer for the predators. However, maybe a more pragmatic choice for us was to use the WildObs national model due to the consistency across all of the 3 species of interest. So for us, a validation workflow is really just a set of repeatable instructions that we can provide to a staff member or a volunteer when they're undertaking the task of reviewing the AI model predictions and correcting any errors. And it enables a targeted and efficient approach informed by the model evaluation results. And we anticipate the need to design one of these workflows for each of our monitoring programs, and that will depend on the performance of the model for that set of species in that particular location. So the steps might look something like this. Firstly, we would want to review the model predictions of the target species, the cats, foxes, and rabbits, and make any corrections to the false positives. We would then want to review the low confidence predictions of dingoes and dogs, because in our report, it showed up that these were often misclassified images of foxes. And we would want to review the model predictions of bandicoots. In fact, bandicoots are not present on the reserve, and we found that in our report, they were often misclassified images of rabbits. And we can also use this sort of workflow to create that positive feedback loop to improve the future model versions. So by supplying additional example images of each of the species, that enables the WildObs team and other model developers to draw from a larger pool of images to create the next versions of the models which will perform better. So the WildObs tagged image repository is a great facility to enable that capability. Some future enhancements that we're working on in this workflow. So version 2 of the model evaluation tool that Renuka and I are working on will include the model confidence scores, and this will enable improvements to the design of that validation workflow to make it really granular and targeted. So the summary points. We're finding that the AI models can significantly speed up the image review process if we use them correctly. And evaluating the model performance enables us to select the best model available for a given location and the set of species, and to design that targeted validation workflow to account for the errors in the model. And by sharing more of our data for training purposes, we can create that positive feedback loop and accelerate model development. And now I'm going to hand back to Matthew.
Thank you. Now I'm going to do a quick overview of some work we did to develop our own classifier in collaboration with Renuka and another collaborator named Prakash. And so this came from a variety of collaborators all sampling in the same region and realizing we probably had enough um, tagged images because we were previously doing this tagging on a different platform before WildObs existed. And so we had all these tagged images, which we can download automatically, for example, from Wildlife Insights. If that's where you keep your tagged images, we can easily scrape all that. And then we passed it to our computer scientists, so Prakash and Renuka, and they built us a model. Let me show you how that works. So this is the wet tropics. Go slide so we get the full picture. Keep going. There we go. It's way up there in northeast Queensland, and it's biodiversity hotspot. And all these data sets are present in the WildObs database. There's actually screenshots from the WildObs database. And so by the time Sky, a PhD student, wanted to continue sampling up there, we thought, hey, let's train a model so that you don't have to manually sort 500,000 or million images. So we went and got all the previous tagged images, and we went through this process, which was capture the images, upload them to the cloud, we annotated them, and then we had our true data. Then we tried training models a variety of ways. First, we did a local model, and then we did a local model means we built it using only the pictures that we had. Then we did a system called fine tuning. And this means we took an existing model that performs pretty well, but didn't include our species. Like they weren't classes in that model. That is usually called species net because that's a general model that was fine-tuned already to wildlife, but it doesn't have a lot of Australian species. So then we fine-tuned it further with our set of species that we had a lot of images of. And then we tested the local model versus a small version of the species net fine-tuning model versus a larger set. And what I mean larger is how many training images did we use? And the results were positive. So what these plots are showing is the green line is our fine-tune model, and it always outperformed a local model when we try to build it without using one of these existing architectures. So SpeciesNet is called an architecture. There's other architectures, but we found that this worked really well. So what it means is we can get really great results for our particular species in our ecosystem using the knowledge from global models and fine-tuning it to our local system. So that was a great result for us. This is in a manuscript, and if you would like to read about the process, you can just send us a message and we will share the PDF of this. And yeah, we'll send a message out when it gets accepted, hopefully. Okay. Next, there we go. So now we had this computer vision model. And then we went out and we collected, mostly Sky, PhD student here at UQ, she collected a absolute phenomenal amount of data. I think 300 cameras, almost 1 million images. And so we used the WildObs image management platform to bulk upload them. Then we selected the new model we just trained that we already put on that platform. And then Sky actually recruited a bunch of her friends, some undergraduates, and some collaborators to all come sort or tag these images, so verify the images at the same time. And this is enabled because we have a cloud-based system, so everyone can log in and simultaneously be working, including working together, like we had pizza parties where everyone came and did it. And so it really just shows the power of these cloud-based systems to make spreading the workload easier and more enjoyable. All right, now I'm going to hand it back to Renuka to say how this little case study can be expanded and scaled up for the rest of Australia.
Thanks, Matthew. We are building, it's already complete, the cloud compute for our production-ready environment. It will be backed by high-performance GPUs, and the ideal peak throughput would be 24K to 40K images per hour. You will be able to complete the analysis of around 1,000 images in around 2 minutes, and for around 1 million images, it will take 2 to 4 days. This is our prediction, and we have been testing this platform rigorously. This is provided by our collaborators from ARDC, Nectar Research Cloud. We are really thankful to them. In terms of future classifier roadmap, we already have WildObs with Tropics model, WildObs Gari model into the platform ready for you to test. We're also going to import the Parks Victoria model developed by AlexAI and the Tasmania model developed by Barry Brook from University of Tasmania, Western Australia model when it's ready. We have developed our own WildObs national model onto the platform, and also AWC 135 developed by Australian Wildlife Conservancy. It's also available onto our platform. Coming to how we train our computer vision models. What we need the most is good quality and quantity data. It has to be varied in terms of the species coverage and environment coverage and habitat coverage. After I get a balanced set of that data, then we choose the right models and the compute. Right now, we're using the compute from ARDC Nectar, and we train the models, and the goal is to have high-performing, highly accurate models, and also it should have low latency and follow up with our resource limitations. If we are not satisfied with it, we go back to curating much better data set. Right now, we are relying on our WildObs tagged image repository to get this data, and it is a bit biased towards Queensland at the moment. That's why we are very keen for you to share your data with us and help us build much more structured data set so that we will be able to build better performing models for you, and happy for you to use our platform. The final takeaway for this presentation is the best model that you will choose is the one that works for your data. There's no generalized model that will work best for all of the use cases. So with this, the steps that we have mentioned and also the user studies that we have shown you, you will be clear on how to curate your own small data set and assess what model performs best for you. And after you have finalized that model, the classifier, you will be able to do the bulk uploads onto the platform and get the analysis. What's next for WildObs? We are going live on June 1st, and in June we have REST-BAS workshop coming, so you can attend those and see how the platform is actually working. Some of us will be there to assist you with the training sessions, and lots happening throughout the year. We are uploading training materials onto our website, and we have onboarding support, and happy to take questions now. Thank you.
Thanks, Renuka. That was great. We have a couple of questions. The first one is about sequencing. So camera trap images are often captured in sequences. Is there currently a way to classify on the sequence rather than single image, or aggregate ID confidence to improve confidence of the ID? And that's from Alistair.
Yes, that's a great question. So like I mentioned in the steps that we are following while running the computer vision model, after the detection phase, after you have detected the bounding boxes for the animals, the next step is to track those bounding boxes and create a sequence from that. That way, we are tracking the same animal across the different images that you have uploaded consequently. And that way, it is treated as one sequence and supplied to the classifier for the detection purposes. And it is up to you that how much sequence cutoff you have chosen. You can choose it for 2 minutes or 1 minute. If you choose it to 0, then you will only get the image level predictions. But when you're increasing the sequence cutoff to, let's say, 2 minutes, then with the help of timestamps for every camera trap image, our platform, it is integrated to read these timestamps, and we will be able to collate those images into a sequence and track the bounding boxes from it.
Great, thanks, Renuka. We have another question from Adam, who says this is a great emerging workflow, which is awesome, thank you. And do you plan to expand beyond camera trap data to other ecological imagery? We have a few 100,000 images of vegetation taken continuously along the Australia coastline. We'd love to look at using AI for identifying those features.
Matthew, do you want to take that?
You're muted.
Yeah, the answer is yes. Those are great ideas to look at other modalities. But I would say our current focus is for the ma vast majority of users, and especially our government, NGO users, and state and federal government for that matter. So I would say we are looking to do that. We'd be interested in partnering with people if they want to do that, for example, by co-investing in a project. But it's not our immediate focus. But it is interesting. It's something we've talked about. Also, there's lots of great applications to agriculture and livestock monitoring. So there's a lot of ways that these tools can be used outside of biodiversity conservation and management.
Great, thank you. Another question from James, and I think Matthew, you did answer this in the chat, but the difference between the image platform June release and web platform later release, just to make sure it's clear.
Yeah, the web platform was not maybe a great word for that. What we mean is a database web platform where people can go and explore our database. And this is spreadsheets of detections. And you'll be able to view where people set cameras. And if people selected that they want to make their data public, then you can actually see what animals were detected there. After it's all been, of course, filtered for sensitive species, locations to all be removed. And so that's an intuitive way to explore what camera trapping data is available. Right now, you can still do that, but it's through WildObs R. And so that's a R-based platform. So we have some tutorials so you can actually do it quite easily, even if you're not a great, a regular user of R. But yeah, so that's to explore what we call kind of spreadsheet data, the actual where detections happened. If you want to process images, then that's what the image platform is, and that's what we discussed today.
Great, thank you, Matthew. And maybe just a point on accepting both photos and videos, if you want to explain that just a little bit.
Yeah, we accept videos. So videos are a collection of stills. So it's actually not that difficult to take them, and our platform accepts them. So the answer is yes.
Great, thank you. And the final question I have so far is about the pricing. So is it currently free? And if so, is there a threshold or point in time that it will become a charged service? I can maybe take that one. So if you're a researcher and you're sharing your data openly with WildObs, it will remain free. For other sort of use cases where you might need to have closed data and coming from industry, we will likely be implementing a sort of paid tiered service. Yeah.
And I'll just add that for big organizations like state governments, federal governments, even local city councils, if you want to do a co-investment model, that's also been working really well, where we design a project where you get what you want and you support WildObs actually doing a lot of this work. And so there's a variety of ways to contribute. Sometimes it's, cash, but most likely it's through other creative mechanisms.
Great. Thanks. That's all the questions we have so far.
I will, since we have a little gap here, there was something that was really hard for me to understand initially, and once it clicked, it was really helpful in terms of choosing the right CV model. And it was an example where why local models might perform better. And so I'd like you to just think for a second about there being a similar type of bandicoot, like a genus, that's present in nearly every state in Australia, but the species in each state might differ. A computer vision model might really be good at identifying that it's a bandicoot, but not be able to differentiate which species it is. So if you have a national model, it's going to not figure out which of the five bandicoot species this particular image is. But if you have a local model where you only have limited to southern Queensland or Western Australia in the North Kimberley area, and there's only one bandicoot present there, then the model will always get it right because the options are fewer. So that's why we've found that when you can have a local model, you often see better performance is because the options available to choose from are limited, especially for species that have, or let's just say taxonomic groups that have many similar species. There's a question. I'll read it. I'll pass it to Renuka. How often do you plan to update the WildObs model or the different models? And I'll pass that to Renuka.
Yeah, that's a great question. We are trying right now. We are relying on our tagged image repository from WildObs to for data. And whenever we get the data from our collaborators, and let's say if I get data for a particular species which is lacking in our model, then I would make it a priority to train the model within the same month. And it really depends on how frequently we are getting the good quality data set and if it is going to help our current existing national model. So for sure, at least 3 times a year, we will focus on giving it another refresh and training it again. Yeah, so far it is trained on the entire TIR that we have, and we are reaching out to our collaborators to get more data.
Yeah, and this is just a call to ask people if you have tagged images, you've done prior camera trapping surveys, maybe they're even on Wildlife Insights or some other platform. Reach out to us because if you provide these tagged images, we can train a model that's going to work really well for you. So, we can only work with what we have. So, in terms of getting more data, which really means tagged images, uh, if you provide them, the outcomes will be much better for your site.
I can see, are there any plans to move towards hierarchical models to get around this location issue? Yes, that's an interesting question. We are actually working on geo-prior capability, incorporating it in our national model, so that let's say every state, on the basis of that, we will have a geo prior. If a particular bandicoot is not present in that particular state, then we won't give that prediction if you have provided the location information correctly for that data point. And this will help us narrow down the prediction to less number of labels rather than trying to predict from all the labels which are present in our national dataset. So this is an upcoming feature that will be incorporated in our national model.
Can anyone hear me? I'm not sure if my microphone's working.
Yep.
Thanks for that. I'm just wondering about, is there issues there in terms of unknown range, in unknown distributions and potentials to pick up species that aren't in your model but are actually present, but they haven't been recorded there before? whereas a hierarchical model will get around that.
Yeah, that's a great point, James. So, this kind of relates to bigger issues about species range maps, including information that's drawn from ALA, the Alice of Living Australia, and their occurrence records. And so, a computer vision model, if you trust it and you don't review any of the images, and then you could get in a situation where you're just accepting that that species was never there. One thing you can do is you can look at your computer vision accuracy outcomes. So you can say which species had a lot of did the model say, I'm not 100% sure about this one. You can review these relatively poor performing species, which is likely where a species that wasn't expected is going to be attributed. Um, so it's a great point. If that's something that you're concerned about, probably means that you need to manually review a few more of the images or types of images. Like if you think there could be a range expansion of an animal that looks like a coal, then maybe go and look at all the coal images to make sure they are, in fact, the species that you were expecting and not something else that got grouped in there. And, more generally, these models are so helpful. They increase your speed of processing things literally 10x, but they're not a panacea, and they're not more intelligent than a user. And so, yeah, your example really just calls into or makes the point that you still need humans to verify things and use your local knowledge.
Yeah, thanks. I take that point, but as Colin mentioned, if you have an emu that's classified as a crocodile, going back and assessing all the quolls to see if there's a different species of quoll doesn't get around that issue. It still means you have to look at everything.
Well, the image being of emo being a crocodile should have a very low prediction value. And what I was kind of referring to is going through those low prediction values is likely going to be where you're going to find species that you weren't expecting. If you have a very high prediction value, there's a better chance that it actually is what the computer vision model thought it was.
Gotcha,
So,
yeah.
but you're right. In situations where you think you're really looking for something that might not be in the model, then that's a use case that might need a conversation with one of the computer vision scientists like Renuka to train something special, or to think about having more verifications than you normally would.
Yeah. Cheers.
Yeah.
And there's just another question on how we define legacy data.
Great. So data can enter WildObs through a variety of ways. The best is natively, and by that I mean it comes from the images into our platform, is curated into CamChapDP format. We store a copy of it, and you get to choose how you want to share it. So that whole pipeline from the image all the way into the spreadsheet is all, kind of within the same ecosystem, so we can verify every bit of it. We can go back and make changes. Another way is if you already have images that have been sorted, you might have a tagged image collection. So you have a whole bunch of images of each of the species. That's legacy data, already happened. You're not going to put it through our image management system because you already identified it. But what you might do is add it to the tagged image repository so that we could make a new model that includes your species or the species at your site. Or you might say, hey, I want to contribute my spreadsheet data so I can meet my reporting requirements, or to make easy collaboration with people, or because part of my government obligations required me to make data public, or my ARC grant. All ARC grants are supposed to be required to make data public. A lot of reasons you might want to do this. So you'd use our legacy data tool to it automatically, when you fill out this questionnaire, it maps your spreadsheet information into a CamChapDP format where it can be ingested, and then we automatically create a report for you that goes through all the different ways that your data can be visualized and checked and the species present, so you can verify, oh yeah, this worked really well. And then as soon as that's done, then you can load up a dashboard on your own computer to actually do analyses and visualize things. So those are the two ways that existing camera trap data that you've already done with it. You're like, all right, you can still contribute to WildObs with that. Great question. That is confusing.
That's all the questions that I can see, so maybe we'll wrap up.
Great. Well, I just want to thank Renuka. She's done such a great job. Also, Jenna for project managing this, and Colin, great speaker with these examples of how Bush Heritage is using these tools. It's just so valuable. So thank you to the whole team.
Thank you, Matthew. Great job.
Thanks, everyone, and thank you everyone for joining. We really appreciate it.